Hello. We'll start soon. Let me just connect the class.
This meeting is being recorded.
Hello everyone, how are you? Good to see you. Happy Friday. It's been a while since we had a class. I guess that's because there was some kind of a mid-semester break, and there was also a day for various kinds of outreach, but nice to be able to see you all again. I guess that means that we're in the second half of the semester too. So today I'm going to be talking about topic in linear algebra. Linear algebra is a subject which I understand is not necessarily covered that early in a lot of curricula, but I just want to double check. I'm going to turn on the chat just so that I can see. Are people here taking a class in matrix theory or matrices and linear transformations, or did you already take, or have you not taken? If you can just type in the chat, that can be very helpful, because then I can go and see what it is. Okay, so we're getting this split here. Some of you are taking, some of you have taken, some of you have not taken. That's no problem. So what we're going to do is we're going to talk about some questions where I'm going to start by prioritizing the ones where maybe it's going to be easier to understand without as deep of a background. And that's no problem. So okay, let's go to the problems. Problems. Where are the problems? Oh, I need to enable my output. One moment, please. Oh, I also realized that last night I was giving a talk on Novid. We don't need that background. Here we go. Okay, great. So let's get some problems. Oh my gosh, I need a haircut. Okay, anyway, let's keep going. And problems in linear algebra. Here we go. Oh yes, this is a good question to start with. I want to do a warm-up. The warm-up is to calculate the determinant of a ginormous matrix. Who wants to try to compute the determinant of that matrix? Raise hand. You computed it already? Rajiv?
Yeah. Well, if you, the determinant is preserved across row operations. And so if you take the second row minus the first row, you get a row of ones. Then you take that row, say minus the third row, you get a row of zeros. The determinant should be 0.
Yes. So the situation here is that when you want to find the determinant, there's two ways. One way is to kind of just go through, it's called cofactor expansion, where you say that thing times the determinant of all that stuff, minus the next one times the determinant of all the rest of the stuff, plus the next one times the determinant of all the rest of the stuff, and so on. You just keep on going. Now that's not super efficient here. Much better is to say that if I have a situation like this, if I just go and replace a row with that row plus a multiple of another row, the determinant is the same. And so what you're saying is that you want to take, let's say, replace the second row by row 2 minus row 1. As soon as you do that, the second row just becomes all ones. Now you have two rows which are all ones. And you're saying, let's just take the third row, replace the third row with it minus the new second row of all ones. Now I've got an all zero row. And when there's an all zero row, when you do this cofactor expansion, you can go across that row of all the zeros. And you're like, that times the determinant of what's left. Oh, but that was 0. So it's like 0 times something, minus 0 times something, plus 0 times something. The answer is 0. Great. And also with a question like this, the reason why determinants are important or interesting anyway is that they're related to solutions of equations, of systems of equations. Oh, did somebody just ask a question? Yosef, are you trying to ask a question or are you trying to answer a question? Maybe not. Okay. Also, maybe I could. Oh, that was for the determinant. Oh, no problem. Sorry about that. Right, it's just that, as you can tell, my vision's not good, so I couldn't tell what the timestamp was. But back to this thing about determinants. Determinants are useful for finding out whether these systems of linear equations are what's called linearly dependent or not. And if you thought about these as coefficients for linear equations, well, I would have 2 out of 3 linear equations, which are really just 2 linear equations, because somehow the sum of the first and third is the second. I put this example here because it's, in fact, a question that is quite related to a question I had when I was a student learning linear algebra. It was on the midterm, and the professor had put a giant determinant to calculate. It was like question 1 or something. It was just, find the determinant of this giant 7 by 7 matrix. Where obviously the answer was 0 if you looked at it carefully enough. But why that was the question was because, well, it was like if you didn't pay any attention during the class, you would just try to do it the high school way, and you'd say, well, there's only 7 by 7. How long could that take? And you just kind of get started. And after a while, you would spend the entire midterm just attempting to calculate this thing out the old-fashioned way, and probably get a 0. So yeah, that's a certain thing. It's like somehow on a linear algebra exam, if you ever see a question of like find an enormous determinant, the answer's got to be 0.
Yeah.
Wait, yeah? No? Okay, no problem. Which takes us to the first question I want to play with. Let's find the determinant of a giant matrix. So this is the first problem on the sheet. We're going to write an n by n matrix, and we'll put that mij is something. Now mij, that means the entry at the ith row and the jth column. Okay, and that entry at the ith row, jth column is supposed to be just the product of some numbers, ai, aj. Except that on the diagonal, when I equals j, what I'm going to do is I'm going to put just ai times ai. Which makes sense. That's actually what you would put anyway on the diagonal if it was supposed to be ai times aj, except that you plus k. Okay, and the idea is to show the determinant is divisible by something, okay, and find its other factor. Now the thing about showing it's divisible by something and finding the other factor, that just means find the determinant, because we have to do everything anyway. But there's a hint that it's going to be divisible by k to the power n minus 1. How can we approach this? I'm going to try to write down this determinant. And then we can look at it. Okay. So, we need to take the determinant of something which looks like a1 squared plus k, a1, a2, a1, a3, and so on, up to a1, an. And then the next row will be a2, a1, a2 squared plus k, a2, a3, a2, an. And it keeps going. And the last row will be an, a1, an, a2, all the way to an squared plus k. And we want to know something about the determinant of this. So those are the two vertical bars I'll write. Are there any ideas on how to approach this? And I actually don't want you to just tell me the answer. I'm looking for lots of little ideas that we can use to put this thing together. Out of it.
So no clue if this will work, but this matrix is symmetric across the diagonal.
Okay, observation time.
So you can like write it as like a product of an orthogonal matrix times the matrix with the eigenvalues times the inverse of the orthogonal matrix, right?
Okay, so it's...
Is that what it is?
Well, can somebody confirm? Please type in the chat if you think that he's right. He's saying you use writable as some p times a diagonal times a p inverse, where d is diagonal.
And p is orthogonal, right?
And p is orthogonal. Okay, if you haven't seen these words before, this is what you will learn in any class that you're taking about matrices at CMU. Don't know what orthogonal means? Yes. So we know what diagonal means. That's cool. Diagonal means that it's like the matrix. Oh my gosh, you did this in 241 today? That's cool. Oh wow, we can use this then. Wait a second. I thought I asked the class last time. I taught this class on Wednesday. Did people learn about eigenvalues already then? How do you learn this without eigenvalues? YH. I don't know enough internet lingo to know what YH means. Oh, YH means yeah. Okay, I've just learned something new. Oh boy. Wait, 242 skipped eigenvalues? How's that possible? Okay. Well, 241 did. That's cool. 242 is going to do eigenvalues. Of course they're going to do eigenvalues in 242. That's like the whole point of linear algebra in some sense. Anyway, you'll cover it soon, but let's talk a little bit about this since not everyone knows what this means. A diagonal matrix is a matrix where the only non-zero entries are on the diagonal. That's cool, right? Everyone's learned this at some point in a matrix class, probably. A diagonal matrix means that the entries on the diagonal are the only ones that could be non-zero. By the way, if it's all zero, it's still called a diagonal matrix. If your matrix is everything is zero, it still satisfies diagonal matrix because at least the stuff off the diagonal is zero. All right? Now that's a diagonal matrix. And diagonal matrix, by the way, they can be different on the diagonal. All right? Next thing is, what's an orthogonal matrix? Well, actually, let's talk a little bit about this, because why not? Let's have some fun. What's an orthogonal matrix? An orthogonal matrix has to have something that feels orthogonal in some sense. Can anyone tell me what it is? And then we can translate that. Raise hand. And this is from Raid. Oh, no. Did I do it right? Yeah, Raid.
Yeah. Yep. I think the property for orthogonal matrices is that Q inverse equals QT.
Okay. I just called it P just because it's there, but Q would have been fine. What's so orthogonal about this? This doesn't look very orthogonal to me. All I see is there's a T here. There's a reason why it's called orthogonal. Out of it.
It's because all the columns are perpendicular to each other.
Yes. So
if you transpose it and then multiply, then you're essentially dotting each column with each other column, and it goes to zero every single time when the two columns weren't the same to begin with, and it's 1 when they were the same column.
Excellent. So the way it is like these are like columns. C1, that's a column. All the way to Cn, that's a column. Okay, so I'm just writing down, here's my matrix. My matrix is P. This is my P. And let's write a P there. That's my P. And here's my P transpose. Now P transpose is going to be P, but transposed. And so that means that the original first column of P became a row. And the nth column of P became a row. And now the beautiful thing is if you do the matrix multiplication, you're actually going to be taking the columns times the transposed columns, which is like the columns back. And the fact that when I multiply this together, I get the identity, it's in fact telling me exactly that if I take the columns, all of the columns, different columns, are orthogonal to each other. Different columns dotted with each other is 0, because those are different, right? What happens is here, this is equal to identity matrix, which is 1, 1, 1, 1, 1, and a bunch of zeros off. And the zeros off the diagonal exactly correspond to grabbing a different column and a different column over here. And you dot them together when you do this, so their dot product is 0. Except if you happen to take the same column and the same column, you dot them together, it's 1. In fact, it should be called an orthonormal matrix, for goodness sakes. But anyway, so this is true. This is a true fact. Maybe it's useful. I should add one more thing. This fact, I believe it requires your matrix to be all real. But in this particular problem, did we know that the A's are real? I'm a little curious. It didn't specify. It didn't specify whether A was real or A was complex. But I'm just going to say this particular symmetric thing, it's in fact only true for real symmetric matrices. But for now, let's pretend that A's are real. Okay, what else can we do? Sana.
So that way of writing it is convenient because the determinant of a diagonal matrix is just like the product of the elements along the diagonal.
Mm-hmm.
And also, I think that the determinant of orthogonal matrix is either +1 or -1.
Okay, the determinant of an orthogonal matrix is equal to plus or minus 1. This is cool. Actually, I should say, whenever I do one of these classes on this linear algebra stuff, I know not everyone has taken all of these things, so I also use this as a chance to maybe discuss some of these facts. The first one, determinant being product of diagonal. Why is that true? That's true because that's just like calculate the determinant the old-fashioned way. This thing times the determinant of what's left. Okay, we'll do that soon. Oh, but everything else is 0. So you're just like plus and minus is 0 times stuff. So actually determinant being the product of diagonals is just, if you try to do it the old-fashioned way, you'd end up multiplying all of those together. That's cool. Does anyone know a good way to know why the second thing is true? You are right. It is true that if I have an orthogonal matrix, determinant is either plus 1 or minus 1. But why? There's an easy way to prove it, actually, based on what we've already seen here. Out of it, I see you raising your hand, so you can just like, yeah.
Oh, okay. So we already know that P transpose has the same determinant as P. So the determinant squared has to be 1.
Yes. So the determinant of a transpose of a matrix happens to be the same as the determinant of the matrix itself. Now, when you use this, now somehow if that was the case, I'll write but. We happen to know that the determinant of the identity matrix is the determinant of P times, well, P transpose times P. And also determinant happens to have the property that you can go with the products. So determinant of two matrices, when you multiply them together, is the product of the determinants. So then that's how we go from some sophisticated concept like an orthogonal matrix, and we can break it apart into some much simpler things, much more simple properties of determinants, such as if you transpose it, nothing happens, and if you take a product, it's the product of the determinants. But now suddenly, how many numbers are there which square to 1? Because these two are the same thing. So if it squares to 1, it's going to be plus 1 or minus 1. So this is plus or minus 1. Or minus 1. Okay, so that was cool. Is there anything else we can do? It is now true that, yeah, if I wanted to, oh yeah, I think Sana is also doing this because you wanted to say, well, I want the determinant of the product of all three of these. So that's going to be determinant of the P times determinant of the D times determinant of the P inverse. And the determinant of the P and the determinant of the P inverse are actually both 1. So it's just, the answer is just determinant of D, whatever that is. What else can we do next? By the way, you don't have to follow this track. There could be a different way to solve the question also. Anyone else want to try? I just want to give other people a chance to try first. And remember, you don't have to go on this track. If you have some other observation, however small, or other strategy you'd like to try, feel free to just suggest. Okay, got somebody else. Right?
I don't think this has been suggested already, but I think the determinant of the diagonal matrix equals the determinant of the original matrix that we're starting with.
Okay, let me record that. That's a very important fact that we can use that comes from here, right? So this is because determinant of the original equals the determinant of PD P inverse, which is equal to the determinant of P, determinant of D, determinant of P inverse, and that's just equal to the determinant of D, because each of the other two things are 1. So let's record that fact. Okay, more thoughts? Again, I want to emphasize that this is not necessarily the only approach we need to use. So don't feel shy if you have something else which is different, even if you think it's elementary or trivial. Otherwise, let's go back to Adivit. Adivit, you had your hand up, right? So I'm curious, what else do you wanted to try here?
So, no idea if we could do this, but maybe we could actually try to find some of the eigenvalues, or maybe guess an eigenvector and find its eigenvalue. No
Okay.
idea. I don't know if anyone has any ideas on what we could try.
Right. So the diagonal happens to be the eigenvalues. And so I just need to find out what all the eigenvalues are. Oh boy. that looks like it. Okay, so this is interesting. Out of it's like, I don't really want to take the determinant. You know, like the problem said, find the determinant of this. You don't find the determinant of this by first saying, write a bunch of minus lambdas here, and then find the determinant of that.
Yes.
Right? Because that's like it would be more work in some sense.
All right.
Right? So you're like, no, I don't want to just go and like do that the normal way. Instead, maybe could I guess? Could I be lucky enough to guess some particular eigenvectors and eigenvalues? If I could guess and eigenvalues, I'd be good. Then those are all of them. That's an interesting idea. Okay, so it's like, can I guess all the eigenvalues?
No idea.
No idea.
But, I mean, another possible approach would be to just try a small example. Maybe try a 2x2 matrix, or maybe a 3x3 matrix. Or something.
Yeah.
See if we see a pattern.
Okay, or try small examples. Actually, I see that somebody else was going to say something. M. Garcia 2. I don't know what is your actual name.
Yeah, sorry, I forgot to.
No
change
problem.
that up. Could we try maybe an eigenvalue of k? So if we had minus lambdas across the diagonal, and I don't know, maybe simplify things a little. I'm not sure.
Did you say try an eigenvalue of k?
Yeah.
Oh, that's really interesting. You're like, I wonder if that would work. Oh, this is really cute. I'm interested. Okay, so let me record Adavate's last idea here, which was like small cases. When in doubt, small cases. We may have to go there. Okay, small cases, see if we can find something there. But instead you were going to go here and you were like, I wonder if k is an eigenvalue.
Yeah.
Because you're like, if I was trying to find k to be an eigenvalue, I've got this matrix and I would be subtracting k from everything. And my question would be, after I subtract k from everything, does this become singular? Okay, and even if you aren't quite taking eigenvalues yet, let me dig into this and say what we're doing. All right. Idea 9. So what we have here is we have this big matrix. I guess let's give it a name, capital A. Oh, M, capital M. M is equal to that big matrix. I'm just writing big. Okay, and what you're saying is that lambda is an eigenvalue. If you've never learned what this means before, you're about to learn right now. So lambda is an eigenvalue of M with, actually it should be the other way around. V is an eigenvector of M with eigenvalue lambda. Okay? V is an eigenvector of M with eigenvalue lambda if you happen to know that mv equals lambda v. Except that whenever you do this, you actually have to do it with v not 0, or else it's trivial. If v is allowed to be 0, of course m times 0 is lambda times 0 for every lambda. So, and v is not the 0 vector. Okay. So now, why is this interesting? This is interesting because mv equals lambda v is the same thing as, remember, lambda is just a number. Lambda is like some simple number. It's not a matrix. This is the same as m times v equals, now we'll use lambda I times v. And I want to indicate m is a matrix, lambda I is a matrix also. The lambda was not a matrix. Lambda was just a number. And now if I've got these two matrices, mv equals lambda iv means the same as the square matrix. This is a square matrix. M minus lambda I times v equals 0. I guess I don't need these parentheses. Times v equals 0. Are people following? I made a matrix which was m minus lambda times I. And if only I could find some v for which this matrix times v equals 0, then v is an eigenvector. And you want it to be like, I wonder if k works. What about lambda, what about k as a choice of lambda? K for lambda. Because you were like, let's look at that previous matrix. Can we find an eigenvector? Can we find a v that works? Well, let's try. So if I subtract the k, right, if I subtract this k times I, then I get this m minus k times I. That's a square matrix is equal to, well, we have a1 squared, a1, a2, dot, 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 a1, an, a2, a1, a2 squared, dot, 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 a2, an, all the way down to an, a1, dot, 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 an squared. I like to draw my matrices in boxes. Raise hand out of it.
So this matrix, pretty sure, is definitely singular, because take a2 times the first row, and that's equal to a1 times the second row. And like you can do this for like pretty much anything, so it's like really singular.
This matrix is like super, super singular. Whoa.
Yeah, you can pull out like an a1 to the nth power, a2 to the nth power. Right? Isn't that how it works? Can you, if you pull a factor out of each row?
Ah.
How does that mess with? Doesn't that mess with the determinant in a certain way?
Yeah. So the thing is, like, you're like, I want to know if these are linearly dependent, these rows. If I want to know if they're linearly dependent, I could divide out some common factors. If you just took a1 out of everything here, you'd get a1, a2, a3 up to an. If you took a2 out of everything here, you get, oh, again, a1, a2 up to an. Basically, the first two rows are linearly dependent. Okay, then could you maybe tell me a v that works? We should be able to make one. Or is it like there's a bazillion v's that work?
There are just a ton of them, because the determinant is 0.
So the determinant being 0 alone doesn't give me a ton of them. There's a way to make a determinant 0 just by making the first two rows the same. What you're pointing out of it is like, actually, basically all the rows are the same.
Yeah.
You basically have one vector here, but scaled. Do people see that? Like what's going on here is I've got like one vector. It is the a1, a2 up to an. That's my one legit vector. And then after that, I just took that one and I copied it with lots of different things multiplied to it. This is pretty interesting. Okay. Actually, this is going to give you a solution that I did not expect would ever work. That's cool. Sorry, I'm just like, that's cool. I didn't know you could solve the problem this way. But that's because I have an idea in my head. But that doesn't mean that we've all solved it together yet. Okay, so there's like a bazillion eigenvectors. Wait, and also I didn't expect you to solve the solution. I didn't expect you to get this far with eigenvectors, to be perfectly honest. I thought it would be a dead end. But now I'm not so sure it's a dead end. I think in fact it might work. Maybe. It might work, it also might break at the last step. Okay, let's see what other people have in mind. Rajiv.
So yeah, I mean, I guess if we were trying to find a vector, we could consider the sort of the solution to the system if we were to like create three variables. If we just had like, you know, a1, a2, dot, 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 an times some x equals 0, and then the rest are rows of zeros. And so you could like parameterize it basically, where you get, you know, you set all the other ones equal to like free variables, some parameters, and then you express the first element in terms of the other ones.
Yeah, so this is amazing. I just didn't expect this to work at all. All right, so what's going on here is like, because all of these are actually the same, there's a notion in linear algebra called the rank of a matrix. Are people familiar with this? Can someone quickly say what is a rank? What's the rank of a matrix?
Number of linearly independent rows.
Number of linearly independent rows, also the same as the number of linearly independent columns. And the rank of this particular matrix is actually like 1. Sometimes it's 0, but only if the A's are all 0, which is kind of dumb. Okay? But it's effectively like 1. It could be 0 if like all the A's were 0. Let's worry about that separately. But the rank is basically 1. Now, if the rank is basically 1, there's something very interesting, which is that, oh, this is cool. We're basically having a review of all kinds of linear algebra now. And yes, we'll do something with the eigenvalues and the eigenvectors, but right now we're just talking about the beginnings of a linear algebra class. And here we're saying that, look, the rank of this matrix, rank of the matrix m minus ki, is equal to 1. And I want to now use this to review some stuff that you might have remembered, might have learned earlier in any of the matrix classes. You see, we were interested in like when is this thing times a vector equal to the all zeros? Because that's what I'm going for here. This thing times a vector equals to all zeros. That happens exactly when like just the first row times the vector is just 0. Okay? So the neat fact is that m minus ki times a vector v, or you called it x, okay? X equals 0 exactly when, just take the first row, a1, but not just the first row with no multiplying, a2, an times your x equals just 0. I'm going to pause here and just make sure everyone agrees, because I'm going along a track that I wasn't planning to show you, and I could also make a mistake. Does this yellow statement make sense to people? Yes? Right? Because it's like, look, if and only if exactly when's a very strong statement, but it's like, look, if the first thing was true, then the second thing is true, because it's just like divide by a1 or something. Let's pretend they're all non-zero for now. We can think about the zeros later. But if they're all non-zero for now, definitely it's like, if this guy is 0, well, if I just divide the whole first row by the a1, then I get the second thing. And if I get the second thing, I also get the first thing, because every single row just happens to be this thing multiplied by one of the a's. That's cool. So you're like, I only need to worry about this. And now we're going to talk about like dimensions, because this is something people probably have learned before too. It's like, I have this k here. K is my eigenvalue I'm playing with, right? And the question is like, how many different eigenvectors does it have? So what does it mean, how many different eigenvectors? Well, I said an eigenvector is something which happens to have the eigenvalue lambda if mv equals lambda v. Okay. Well, how many? There's infinitely many. I can take a v and scale it by anything I want. If I had a v that worked, 2 times v will also work, because m times 2v is of course going to be double of lambda times v, which is lambda times 2v. So any eigenvector that works, you can always scale it. But the important thing here, oh yeah, Adivit, are you about to say something?
Oh, no.
No, okay. I was gonna talk about how do you count? How do you count how many solutions there are? I don't want to count the number of solutions of v just by how many there are, because the answer is infinity. What's the right way to count in linear algebra? I want to get more people involved in the conversation. Matthew, what would you use?
They have to be linearly independent, right?
Well, yeah. Well, the point is like, so that you don't get a dumb answer called infinity, right? It's like, let's count how many linearly independent ones there are. What's that called? That's actually a word in linear algebra.
I forget.
I forget. Yes, and this is basis. Erica, yes, basis. Right. So it's like we could make a basis for that space. But if I want a number, what's that number? The number has a name. Dimension. Yes. It's a dimension. So what we have here is like, by the way, the x's that work for this, the x's that are the eigenvectors, they actually form a subspace. They are in fact what's called the null space of that particular matrix. Is this ringing bells of people who are taking these classes? Yeah, it's like a null space. Basically, today's class is a ginormous overview of what you've done so far in your class, of like all these different topics, right? So it's like, how many x's work? The number of x's that work is the dimension of the null space. Is it even called the kernel? Do you guys call it the kernel yet? Or do you guys only call it the... You do! Okay. Dimension of the kernel, dimension of the null space. And why did I write the rank? This is another review. I wrote the rank because there's something about the rank and the null space dimension and stuff. What's that? Out of it.
Because, the rank of the matrix is like n minus the dimension of the null space. Like the null space just makes up whatever else is left.
Yes, cool. I'm by the way, I'm doing this because I'm trying to review all of these different concepts that you're seeing in these matrix classes, right? So somehow exactly when this is true, and somehow the rank is 1, all right? And so somehow the dimension of the null space, dimension of the kernel is n minus 1. Why did I get excited about that? There's a reason I got excited about that. It's like, so here's something, right? I've got this thing, and it happens to have, in fact, it happens to have n minus 1 dimension dimension of solution space. By the way, I'm just going to assume that all the a's are not 0. Let's assume that the a's are not 0. Why is that interesting? Raise hand. I need to read. Aryan?
Yeah, I was gonna say that means that the eigenvalue k has multiplicity n-1.
Okay, so not completely yet. It has multiplicity at least that. I'm not sure if you guys have learned this yet, but it is possible to have a situation where an eigenvector has a certain multiplicity, but it doesn't have an eigenspace with the full, with that full multiplicity. Is this something you guys have seen? It's like algebraic versus geometric multiplicity. Yeah, something like that. It's because the multiplicity of the eigenvalue is actually the number of times it's the root of a particular polynomial. And all the multiplicities of the eigenvalues always add up to n. So I'm sorry, now we're actually diving into things that apparently only 241 people have seen about the eigenvalue stuff. But the thing is that there are going to be, if you count up all the multiplicities of all the eigenvalues, it's always going to add up to n. Just for completeness, I'm just going to say a little bit of that because we might actually use this, okay? So 12. So somehow, remember what we were just talking about, the eigenvalues? This is a crash course in linear algebra now. Let me go back here, right? It's like lambda is an eigenvalue if there is a way to find something such that the m minus I lambda times that something equals 0. Well, let me finish this. This means if and only if the determinant of m minus lambda I equals 0. And this is what you use in a linear algebra class to go and find out what are all the eigenvalues. You just solve determinant m minus lambda I equals 0. Or lambda I minus m equals 0, whichever you prefer. And when you solve for this, you end up getting a polynomial of degree n, and you find the roots, and there's going to be, like with multiplicity, adding up to n. And here we already got n minus 1 of them. Okay, that's really cool. I got n minus 1 of them, and oh yeah, when I said multiplicity, you're not always guaranteed that you'll have a root with that multiplicity. Except that there's a useful theorem here, which now I want to double check. In 241, did you actually just talk about this theorem about how a symmetric across diagonal rail matrix gives you this? Yes, this morning. That is so awesome. So if you did that, do you remember any other things in this theorem? It's like, or anything that's useful about the multiplicities of eigenvalues and the dimensions of the eigenspaces? Was anything said about that? Because it turns out that this result, is related to the fact that for every multiplicity of an eigenvalue, you actually have, so for every eigenvalue, you actually have an eigenspace, a space of eigenvectors whose dimension matches that multiplicity. So in fact, over here, what you get is, in fact, it does, this is like, there is an eigenvalue k with multiplicity n minus 1 just from this fact. If all the ai's are not 0. We'll have to worry about ai's being 0 later. Okay? So in fact, this thing gives me, because of the symmetricness, let's just use another thing. By the way, I will talk about how to solve this a totally different way, a more elementary way later. But symmetric is going to imply that actually, symmetric matrix is going to imply that you have k as eigenvalue of multiplicity n minus 1. Okay. But now the important thing about the, oh yeah, Adivate? No? Okay, okay. So what we have here is that we have got this eigenvalue of multiplicity n minus 1. But there's something else that's in fact very important about, yeah, there's something else that's also very important. Yeah, Adivate, are you raising your hand?
Oh, yeah, I think I found the next eigenvalue.
Yeah, what's the next eigenvalue? Because that's all I need. If we just get one more, we're done.
If we have the next one, then we're done, right? So
yeah.
What if instead we do negative of the sum of all the squares of like all the AIs plus k, or something like that. It's like before we got rid of the k and made it a1 squared plus, just made the whole first row divisible by a1.
Yeah.
What if instead we get rid of all the k's and subtract off some more things? No idea what'll work though.
Okay, but why did you think of subtracting off the sum of all the squares?
Well, because along the diagonal, they're just a ton of squares.
So you just feel like deleting all the squares, but then you'll get a big mess in the top left corner.
You will get a big mess, won't you? Never mind.
That's a very interesting idea. Okay, Matthew Garcia, are you trying to suggest something?
Yeah. What if maybe we subtracted 2k, and then we'd have a bunch of difference of squares along. Oh well, we don't know if k is squared. I mean, we could do, I don't know, minus k squared. I mean, I don't know if that would help being able to factor it or not.
Yeah.
Yeah.
So that might be a little bit difficult. There was something else I was going to go for, which I'm actually curious if this works now. You see, it turns out that this thing here about the symmetric matrices, there's another cool fact, which is that all of the eigenvectors are orthogonal. Did you guys talk about that in class?
Yeah, I think it was like the last thing we proved, maybe.
And that's because that's related to the P being an orthogonal matrix. So in fact, all the eigenvectors are orthogonal. If you've got n minus 1 of them, can we guess an eigenvector? I mean, you've already found n minus 1 of them from here, and the nth one needs to be orthogonal to all of the n minus 1 that we've found so far. Is there a vector we should guess that should be the eigenvector, the last one we're looking for? There's a way to make all these eigenvectors orthogonal. So here suppose I got a basis of this. I got n minus 1 eigenvectors, which all happen to satisfy a1, a2 up to an times x equals 0. And I've got n minus 1 vectors x that satisfy that. Can anyone suggest a vector that might just be orthogonal to all of the ones I've picked? Rajiv?
That was from before.
Oh, that was from before.
Yeah.
Okay. The idea of cross product is cool, except in 3 dimensions you can do cross products. Elsewhere you can't. Adivate?
Could it be any vector that doesn't get sent to 0?
Any vector that doesn't get sent to 0. Again, what I'm saying is well, there should be lots. You shouldn't get that much freedom. That's too much, right? The point is I have a collection of n minus 1 vectors so far. Those n minus 1 vectors are all linearly independent, and they all happen to have the property that a1, a2 up to an times it is 0. I would like to find one more vector which happens to be orthogonal to all the ones I found so far. Sophia?
Would A1, A2 to AN work?
How about a1, a2 to an? Oh, it's orthogonal to them. It's come on, it's just staring at it. That's genius. Yes, that's definitely orthogonal to all of them, because that's how the rest of them were defined. The rest of them were defined as everything orthogonal to that one. So let's try it. I wonder if it works. This is why I was I wonder if this will actually work. As soon as I saw this, I've not done the problem this way. Okay, it might fail, but I'm we found k eigenvalues which correspond to this guy. If I can just find one more eigenvalue, I'm done. And that one would correspond to that last thing. So now let's just multiply for fun. Okay, matrix looks like this. a1 squared plus k, a1, a2, a1, a3, all the way, a1, an, a2, a1, a2 squared plus k, all the way to a2, an, dot, 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 an, a1, an squared plus k. Now I'm curious, what in the world happens if you attempt to multiply this by the a1, a2 all the way to an vector equals. Okay. What happens to the first row? Is this actually any good? Somebody help me out with this. What happens to the first row?
Oh, I think I...
Advait,
So you can pull out an A1 first of all.
you're too fast. Oh, pull out an A1. Why? Let me do it slowly. You're doing it too fast.
Okay. So let's take first row dot the vector.
Yeah, we're
right?
doing it.
So then
A1K.
the first row has.
I'm just doing it slowly, okay? Well, my pen is acting weird today. But we have this thing. Okay, that's the
Plus
first thing.
A1
plus
times A2 squared.
A2 squared. Let's just make sure we got this straight, okay? A1, I'm a patterns guy. All the way
And then
to
all the way down.
A1 an squared. So that's the first, I mean, this is going to be a big, it's going to be a vector, okay? I'm going to have a vector. But what's this?
It's just A1 times sum of the squares plus K.
Cool. So I'll write the answer, I'll write continuing equals. And just to emphasize, this is a vector. Okay, this is a vector. Even though it looks very long, this is a vector. Okay, it's a vector. And then now this thing is going to be equal to, the top is just A1 times, what did you say?
Sum of the squares of all the A's.
Sum of
and
the
then plus
squares
K.
plus a K. Okay?
Yeah.
That's the first entry.
And you get exactly the same thing just with an A2.
It
and
actually
an
works.
A3. It actually works.
It actually works. I just couldn't believe it. I was like, when you guys said that you want to use this real symmetric matrix diagonalizable, I was like, there's no chance this is going to work, but I'll humor you anyway. Okay? But it's like, it works. Because if I do the second thing, I get what is it? A1 squared A2. Yeah, A1 squared A2 plus the next thing is A2 cubed plus KA2 plus the next thing will be like A3, like A2 squared A3. No, A2 A3 squared. Plus, and the last one will be A2 AN squared. And the beautiful thing is that's exactly A2 times the same. When I write same, I mean same is same as that. That's the that's the eigenvalue. So that's equal to just the eigenvalue A1 squared plus all the way to plus AN squared plus K times your original vector. A1, A2, up to AN. Are people following? This is like a not fair way to solve the problem. So what I've just done is I've just found like K is an eigenvalue with multiplicity n minus 1. That's an eigenvalue with multiplicity 1. And so what's the answer?
You're done.
You just multiply them. Is that okay? Like the thing we found before is like by this diagonalizing thing, the determinant is the product along the diagonal, is the product of the eigenvalues. So the answer is actually just the product of the eigenvalues. So the answer is equal to, the determinant is equal to, don't write answer equals to. So the determinant is equal to the product of the eigenvalues, which is just equal to k to the power n minus 1 times a1 squared plus up to an squared plus k. Okay, that was awesome. We have like 1 minute left. I want to just share, if this thing was like, seemed like it was too much high-powered stuff, you can do this without using any eigenvalues and any eigenvectors with a different approach. The different approach would be based on when I'm taking the determinant. If I'm doing the determinant of this, it's actually possible to break the determinant of this down into the sum of two determinants. And I'm just going to write that on the next screen. I'm just going to put this here just for completeness in case for some reason it seems like this was like using things you hadn't learned before. This is all stuff that you will hit at some point about the eigenvalues and eigenvectors. And this thing about like what if things are 0, it's more easily resolved with the other one, with the other approach. But with the other approach, I'm just going to write this down. Okay, and so if I'm talking about the determinant of a1 squared plus k, a1, a2. Oh, I should also say, one way to get rid of this, like, what about the zeros, is that the determinant is actually a continuous function in all of the a1, a2 up to k. And so it's like, if it works for all the non-zero things and it's continuous, it has to be what we just found. That's a neat trick, because the determinant is just going to be a continuous. It's a polynomial if I just go and multiply everything out. But if I want to know what's the determinant of this thing, a2, a1, dot, 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 a2, an, dot, 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 an, a1, an squared plus k, this determinant is always equal to the sum of two other determinants, a1 squared, a1, a2, dot, 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 a1, an, a2, a1, but now I have a2 squared plus k. Basically, I'm just splitting off the plus k on the first one. a2, an, dot, 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 an, a1, dot, 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 an squared plus k. That thing, that wasn't vertical enough, that thing, plus the same thing, just that in the top I have just the k, and then I have zeros. And the second thing is a2, a1, a2 squared plus k, and I'm just copying it, a2, an, dot, 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 an, a1, dot, 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 an squared plus k. Okay, I wanted to just share this thing here. This is a true statement. What I've done between here and there is I've taken the top row and I split the top row into two things that add together as vectors to make the top row. And everything else stayed the same. If you want to know why this is true, you just have to do a cofactor expansion. You just have to kind of expand. You know, the expansion would be that times the determinant of what's underneath. What's that? Well, that is the a1 squared, oh yeah, that one, times the determinant of what's underneath, plus k times the determinant of what's underneath. Does that sort of make sense? All I'm saying is that the way that you're going to do that splitting is that you'd split that one, and I already did it. It's the first one and the second one. And then after that, you just take minus this thing times the determinant of this. Oh yes, somebody said, oh wait, isn't this multilinearity of determinant? It absolutely is. Okay, there are people here who have taken a lot of things. That's the theoretical thing I've just used here. It's the multilinearity of the determinant. But this is really convenient because it allows you to prove the statement by induction. If the statement is that the determinant, right? So the way you can, another alternate way to finish this, which is actually much less technology, is you first do small cases, which is what I thought we'd have to end up doing because I didn't expect this to work at all. All right? But I thought we were going to go fall back and do small cases. From small cases, you can guess. Well, you call it claim, which is that the answer is equal to k to the n minus 1 times the sum of the squares, a1 squared plus up to an squared, and then plus k. That's the guess. Not the guess. You make this claim. And you prove the first one by just like plugging in for n equals 1, which is just a1 squared plus k. Yes, it's there. And then you prove it by induction because it turns out that this guy, this is really convenient. This, if you try to expand, is k times the determinant for n minus 1 of them. Okay, which you use this. And then this one, it turns out to be also possible to do with row operations. But I won't go any deeper onto that. I'll just say this is like another way that you could try to solve the problem. You can try to use row operations on this one to get the last piece you need to add to this thing if you used induction. But I'm just impressed that this thing worked. This is what happens whenever I teach this class. I have some ideas of what I want to show. People propose things, and instead of me telling you there's no way it will work, I humor you, being like, it's not going to work. We're just going to go. We'll learn some stuff about linear algebra on the way, and then you surprise me and it works. So, cool. That's linear algebra. And I guess I'll see you guys next week.
Professor,
Yeah,
I just wanted to
sure.
ask you a quick question.
Let me first say goodbye to the YouTube folks. So